Welcome to TechDaily.ai, the show that's all about cutting through the noise to get you to the absolute core of what you need to know. Today, we're diving headfirst into the incredibly complex and rapidly expanding universe of the cloud. Think of this. By 2025, we're expecting a staggering 100 zettabytes of data to reside there. And right now, 60% of all corporate data is already calling the cloud home. It's clearly not just a place to store files anymore. It's become the fundamental operating environment for, well, nearly every business, big or small. But with that immense scale, that complexity, simply being in the cloud isn't enough, right? We need to actively understand, manage, and optimize these environments to truly thrive, not just survive. So how do we navigate this vast digital ocean without getting completely overwhelmed? How do we make sure our systems are resilient, secure, cost-effective? That's really our central mission today, to give you a shortcut, a deep dive into mastering cloud operations. And before we plunge into these critical topics, a huge thank you to our sponsor for this deep dive, Stonefly.
Stonefly is your trusted solution provider and advisor in enterprise storage, backup disaster recovery, hyper-converged VMware, Hyper-V, Proxmox clusters, AI servers, and SA365. That's their turnkey security appliance. All across public and private cloud environments, they've really got you covered. You can learn more about how Stonefly can support your infrastructure by visiting stonefly.com.
Absolutely. And today, our journey takes us through the critical world of cloud logging, monitoring, and site reliability engineering, or SRE, as you'll often hear it called. Our mission isn't just awareness. It's about getting to a clear, actionable understanding. We're going to explore how to ensure your cloud services aren't just, running, but truly thriving, maintaining high availability, staying secure. We'll unpack the essential metrics you really need to watch. We'll dissect the nuanced but crucial difference between traditional monitoring and true observability. We'll share practical strategies for intelligent cost management, always important. And yeah, we'll even take a look into the future of these practices, especially how AI and machine learning are starting to reshape the entire landscape.
Sounds like a packed agenda. Let's get into it. #tag9, the cloud's grand scale and its hidden challenges. Okay, let's start by grounding ourselves in the sheer scale we're discussing. When we talk about 100 zettabytes of data in the cloud by 2025 and 60% of corporate data already there, it's more than just a massive number. It signifies a complete paradigm shift, doesn't it?
It really does.
The cloud isn't just an option anymore. It's the default infrastructure for innovation, for business continuity. But that power comes with, complexity.
Precisely. And this monumental scale, it instantly exposes the fatal flaws of traditional IT management. Think about it. Our old ways of, checking on servers or manually sifting through log files, they were designed for finite, static data centers, environments where a server was a named pet, right? Unique, meticulously cared for.
Yeah, you knew its name.
Exactly. But in the cloud, instances are like cattle, interchangeable, dynamically scaled, ephemeral. A single microservice might spin up and down hundreds of times a day across totally different hosts. How do you troubleshoot that? How do you find the problem when the server that just threw an error might not even exist a minute later?
Right, it's gone.
It's no wonder a Gartner survey found a staggering 80% of enterprises still feel, and this is their words, completely blind or report significant gaps in monitoring their new cloud solutions. This isn't just an inconvenience, it's a critical vulnerability. It leads to major outages, security breaches, and a fundamental inability to innovate quickly. Legacy approaches, they just stifle the very agility that the cloud promises.
Okay, so if the traditional SSH into a machine and check its logs approach is clearly obsolete, what exactly was the core problem with that mindset when you're dealing with literally thousands of VMs, countless databases, intricate network components spread across multiple global regions? It sounds like trying to understand a complex orchestral piece by only listening to one instrument at a time, and that instrument keeps changing.
That's a perfect analogy. The core problem is the sheer volume, velocity, and variety of data generated by a modern cloud environment. That's one piece. The other is its distributed and ephemeral nature. If each service maintains its own siloed log files, or if your monitoring is limited to basic CPU and memory on individual VMs, you completely lose the thread. You lose the context of what's happening end to end.
No big picture.
None. You can't trace a user's request across, say, 50 different microservices if you're stuck looking at log files on individual machines that might have disappeared moments ago. You need that conductor score, that holistic, correlated view. And this is where cloud logging steps in. It's the absolute cornerstone of insight. It provides that score. It's about much more than just collecting text files, though. Cloud logging is the strategic process of centralizing, aggregating, and intelligently managing logs from all your diverse cloud sources. Its core function: to collect, correlate, and analyze these logs from across your entire technology stack. This lets you rapidly identify performance bottlenecks, accurately measure system performance, and fine-tune configurations to prevent issues before they happen. Fundamentally, centralized cloud logging is crucial for security, for the long-term health, and for the optimal utilization of all that data you've entrusted to the cloud. Without it, you are, quite literally, flying blind in a constantly shifting landscape.
So if cloud logging is that cornerstone, it brings us to a trio of terms we hear constantly: logs, metrics, and traces. Now, for our informed audience, we know they're distinct, but where do teams typically struggle to, really grasp their unique purpose? And why do we absolutely need all three for that comprehensive understanding in these complex cloud systems?
Yeah, that's where the nuance really lies and where things can get confused. Many teams still treat them as somewhat interchangeable, or maybe they over-prioritize one, missing the complementary power they offer together. Think of your cloud environment like a high-performance distributed system, maybe like a global logistics network. First up, metrics. These are your health gauges, your key performance indicators, your KPIs. In our logistics analogy, metrics are the real-time status updates. Number of packages processed per minute, average truck speed, warehouse temperature, things like that. They are point-in-time measurements about the health and operations of a component or a system. Critically, metrics are compact, very small. That makes them incredibly efficient to collect, even at massive scale. And because they're small and can be pre-aggregated, they are perfect for automated alerting and dashboards. If package processing drops below a certain threshold, boom, a metric can trigger an immediate alert.
So a server CPU usage spike, network latency, database connection, those are all metrics, quick signals.
Exactly. They tell you that something is happening or what the current state is quickly and efficiently. Quantifiable signals. Now, logs. If metrics are the status updates, logs are the detailed event diary for every single package and truck in that network. They describe discrete events that occurred within components. So while a metric might tell you the package's processed rate dropped, a log provides the rich, detailed context. Error. Package 789 failed customs check due to missing declaration, or maybe truck hashtag 345 encountered unexpected road closure, rerouting.
The specifics.
Right. Logs are often much larger than metrics, which makes them less ideal for those real-time system health checks where efficiency is paramount. Their primary use comes after metrics have flagged a potential problem. You then filter through the relevant logs to understand what exactly happened, who initiated it, and why it failed.
Okay, so when a metric screams problem, the logs fill in the narrative. They give you the granular details about that specific incident. It's the why and the how behind the what.
Precisely, the context. And finally, we have traces. If metrics are the gauges and logs are the diary entries, traces are the end-to-end journey map for one specific package from sender to recipient, noting every single handoff, every transit point, every delay. Tracing provides a continuous view of an application following a program's flow and data progression from start to finish. Its purpose is really optimization-focused. It helps you understand a single user's request as it travels through your entire, often distributed application stack. A distributed trace is essentially a collection of spans, where a span is the smallest unit of work, like an API call, a database query, maybe a message pulled from a queue. It's like seeing the exact path and, crucially, the timing of a message from the moment it enters your system until it's fully processed.
Wow, that sounds incredibly powerful, especially for microservices. If a user's request is slow, a trace can literally show you every step, how long each step took, maybe even the parameters passed between services.
Exactly. It's amazing for finding those hidden bottlenecks.
But what's the biggest hurdle teams face when trying to implement this kind of distributed tracing? Getting that full end-to-end lineage sounds complex.
It is. The biggest hurdle is often instrumentation. Getting every single service, potentially across diverse languages and frameworks, to correctly emit trace data with consistent identifiers, that requires significant upfront engineering effort. And you need strict adherence to standards, like using trace IDs consistently. It's not just about turning a feature on, it's about making sure every piece of your distributed puzzle is contributing its part to the overall journey map.
Right, requires discipline.
It does. So when it comes to strategic data usage, the guidance is pretty clear. Use metrics to track event occurrences, count items, measure time taken for actions, or report current resource values like CPU or memory. These are your efficient, real-time alerts. Use logs for the detailed information about an event that's also monitored by a metric, especially for errors, warnings, or other exceptional situations. That's your forensic data, your context. And a trace provides that vital visibility into how a request is processed across multiple services. Absolutely crucial in today's complex microservices environments, with each trace needing a unique identifier to stitch that journey together. That's your end-to-end story. Leveraging all three cohesively, that's the real key to achieving true observability.
Okay, with all these data types, logs, metrics, traces, it can still feel like, well, drinking from a fire hose, right?
Yeah.
For our audience navigating these complex cloud environments, what are the absolute core cloud metrics, the ones that truly form that essential early warning system? Where should you focus your attention first to ensure workflow efficiency and system health without getting totally lost in the noise?
That's such a critical question. The signal-to-noise ratio is everything here. You can track thousands of metrics, but honestly, a handful are truly foundational for predicting and preventing issues. First, you absolutely must track requests per minute. This metric isn't just a number, it's the pulse of your application. It reveals the real-time demand on your cloud environment. If you see a sustained spike, you know it's probably time to consider scaling up resources. If it dips unexpectedly, well, that might indicate an issue preventing traffic from reaching you, or maybe an opportunity to scale down for cost optimization. It's fundamental for understanding load and capacity planning.
So it's not just reacting to overload, but also proactively scaling resources up or down based on actual demand. That optimizes both performance and cost. That's a crucial differentiator.
Exactly. Proactive, not just reactive. Next, consider time to acknowledge. This is the time it takes for your cloud-based application, or maybe more specifically the infrastructure in front of it, like load balancers, to initially respond to a request. Just the handshake. A slow acknowledgement time often points to problems with those load balancers, maybe network congestion or issues with how requests are being routed. It's often the first sign that traffic isn't even reaching your application effectively.
The front door is jammed.
Precisely. And a critical best practice here is to compare this time to acknowledge across different cloud regions or availability zones. That can help pinpoint localized latency issues really quickly. Closely following that is response duration. While time to acknowledge handles the first handshake, response duration measures the time it takes for the application to actually complete the work and send back a full response after acknowledging the request.
Okay, the actual processing time.
Right. This is your direct measure of whether your application itself has sufficient resources, CPU, memory, database connections, to process the current traffic load efficiently. A low response duration indicates efficiency. A consistently high duration, that's a clear signal to allocate additional resources to prevent user experience degradation.
That's a powerful distinction. So time to acknowledge flags issues with the delivery route, the infrastructure, while response duration flags issues with the application's capacity to actually serve the request once it gets there.
Yeah.
Great for troubleshooting.
Exactly. Next up, error rates. This metric, simply showing how often a request results in an error, is your immediate health check. It reflects the health of both your cloud environment and the applications running on it. A sudden jump in errors, whether they're 4MicX client errors or 5MicX server errors, is like a flashing red light on your dashboard. It demands immediate attention. It often signals a deeper underlying problem, anything from misconfigurations to application bugs or just plain resource exhaustion.
Can't ignore that one.
Definitely not. And finally, server node availability. For any distributed cloud environment, you absolutely must track the percentage of available servers or nodes within your clusters. There's a widely accepted rule of thumb. If your availability falls below, say, 90% of your total deployed servers, it could indicate serious widespread problems with your instances. This isn't just about individual machine health, it's about the resilience of your entire infrastructure backbone. Losing too many nodes can cascade quickly.
Right. So the collective power of these 5 metrics, requests per minute, time to acknowledge, response duration, error rates, and availability. It isn't just about spotting trouble after it happens. It's about anticipating growth, predicting potential issues, even security challenges before they fully manifest. It sounds like it turns observation into true strategic foresight.
That's the goal. It allows you to proactively manage your cloud's health and performance rather than constantly firefighting.
Okay, that brings us to a really crucial distinction. We've talked about logs, metrics, traces, and those essential early warning metrics. But the real question for managing these complex systems is traditional monitoring actually enough anymore? Or do we need something more? to truly handle the complexities we're discussing.
Huh.
What's the fundamental difference between monitoring and this term we hear more and more, observability, and why does that distinction matter so much in the cloud?
Ah, yes. This distinction is absolutely paramount in modern cloud operations. They're related, but definitely not the same thing. Monitoring is primarily reactive. It focuses on predefined metrics and known thresholds to track the health of a system. It tells you when something is wrong, usually identifying issues after they've already occurred. Monitoring tools visualize data on dashboards, they set alerts for known failure states, and maybe logs provide some context after the fact. It's like a car mechanic who only knows there's a problem when the check engine light comes on. It's effective for known, anticipated problems, but it's limited by system complexity and less effective at predicting new or unknown issues.
The known unknowns.
Exactly. Observability, on the other hand, is proactive and far more powerful. It goes beyond simply monitoring known metrics by allowing you to infer the internal state of a system from its external outputs, meaning all those logs, metrics, and traces we just discussed correlated together. Observability doesn't just tell you when something is wrong, it aims to tell you what, why, and how issues occur, often identifying and helping you address them before they impact your users. It often leverages advanced techniques like AI and machine learning to analyze massive correlated data sets. It produces actionable insights, it can predict issues, and sometimes even recommend or create automation to prevent them. It's the mechanic who understands the entire engine, can listen to subtle noises, predict potential failures based on patterns, and even suggest preventative maintenance based on nuanced readings, not just the warning lights.
That's fascinating. So while monitoring is about watching those known unknowns, observability is really about identifying the unknown unknowns issues you didn't even know to look for until the system tells you through its combined outputs. What kind of real-world impact are you seeing from companies that truly embrace observability? Is it making a difference?
Oh, the impact is profound. We see examples like ANZ Bank, a major bank, using observability for the entire life cycle of its mobile app. They ensure it's highly performant and secure across all user interactions, which is critical for their business. Or look at William Hill, the betting company. They leveraged observability tools to improve their mean time to resolution MTTR by a staggering 80%.
80%.
80%. And they could resolve critical P1 incidents in under 60 minutes. That's a massive impact on business continuity and customer satisfaction. It's because they moved from just seeing the check engine light to understanding the precise engine problem and how to fix it almost immediately. That's the power.
Huge difference.
Now, shifting gears slightly, when it comes to successful application migration strategies moving apps to the cloud, whether you're doing a simple lift and shift or a more complex re-architecture, there are several best practices to follow for a smooth transition. First, and this is often missed, start your baselines from the end user's perspective. Before you move anything, measure your application's performance from the viewpoint of your actual users. What's their response time? What's their error rate? How long does it take to communicate with external services they rely on? If you only focus on individual back-end component metrics, you can create huge blind spots around crucial elements like network latency or load balancer issues that directly impact the user, even if the server CPU looks fine.
Measure what matters to the user first.
Exactly. Second, benchmark selectively. If it's a straightforward lift and shift, okay, compare the same critical metrics before and after in the cloud. But if you're re-architecting into microservices, don't get bogged down trying to duplicate baselines for every tiny microservice that no longer aligns perfectly with the old monolithic architecture. Your primary concern should still be that overall end-to-end user experience. That's what impacts your business goals. Third, and this is crucial, prepare for breakdowns. Just assume something will break during the migration. It almost always does.
Murphy's Law.
Pretty much. You need to instrument your entire stack, front-end, back-end, and infrastructure before you migrate, so you can quickly identify and fix problems when they pop up. Get familiar with normal behaviors in the new environment so anomalies jump out immediately. Distinguish real issues from just expected cloud dynamics or temporary glitches. Fourth, a perhaps controversial one, don't bother baselining on-premise infrastructure in isolation. It often yields very little practical value. If your end-user experience improves post-migration, then the fact that underlying infrastructure metrics like CPU or memory utilization changed is often less critical. You're usually seeking different performance characteristics and efficiencies in the cloud anyway. Focus on the outcome.
Focus on the user experience and business value.
Right. Fifth, and this is a big one specifically for the cloud, treat cost as a metric. With the cloud's seemingly infinite resources, it's frighteningly easy for costs to spiral out of control if you're not watching. Monitor your cloud costs and budgets just like any other performance metric. Integrate cost tracking directly into your performance dashboards. This helps prevent unnecessarily large bills and ensures you're using resources efficiently. You want to pay for the value you get, not for waste.
Essential discipline.
Absolutely. And finally, don't discard your hard work after migration. Once you've established solid baselines and the ability to debug effectively, retain them. Leverage these established baselines with alerts and dashboards to detect future regressions and maintain that consistently great user experience you work so hard to achieve. Your investment in baselining should pay dividends long-term, not just be a one-off migration task.
That's a really comprehensive approach to migration. In your experience, which of these migration strategies do organizations most often overlook or maybe shortcut, and what's the typical fallout when they do?
I'd say far too often teams neglect that very first point, starting baselines from the end user's perspective. They'll meticulously measure server CPU or memory utilization on-prem, then measure it again in the cloud. But they forget to gauge the actual user experience before and after the fallout. They might declare a migration successful because the backend metrics look okay or even slightly better, but then they find out users are experiencing higher latency or more intermittent errors, maybe due to subtle network shifts, inefficient API calls between new services, or load balancer configurations that were never measured from the edge. It creates a critical blind spot that impacts perception and satisfaction.
Right. It works on my machine problem, scaled up.
Exactly. And when things do go wrong, as they inevitably will even post-migration, that traditional SSH into machines and sift through logs just won't cut it, not in these ephemeral, dynamically scaled, microservices-rich cloud environments.
So what are the modern strategic best practices for troubleshooting in this new landscape? How do you debug effectively?
You're absolutely right. The old ways are not just inefficient, they're often completely impossible. Modern cloud troubleshooting demands a different mindset and fundamentally different tools. First, a critical mindset shift. Monitoring is not your core business. Unless you are a monitoring company, your business doesn't gain value from you building a complex, custom, homebrewed monitoring solution from scratch. Invest in robust vendor solutions that focus on monitoring full-time. They offer massive scaling capabilities, enterprise-grade security, and broad technical knowledge across a wide array of technologies that you simply can't replicate efficiently in-house. Let them handle the monitoring infrastructure so your engineers can focus on your product.
Focus on your own value proposition.
Precisely. Second, be ready for deep dives and horizontal debugging. In distributed microservices architectures, you need tools that give you that bird's eye view first. Something to quickly pinpoint anomalous components or dependencies across tiers. Only then can you effectively zoom in for the granular details, understanding the connections and the full blast radius of an issue. Think of things like service maps or health maps that visually show connections and statuses, allowing you to trace that user request across the entire distributed system.
See the forest before examining the trees.
Exactly. Third, collect meaningful data. Don't take shortcuts here thinking you'll save a few pennies on storage. In the cloud, you generally want to collect every bit of relevant, unaggregated, and multidimensional data you can, high cardinality data. This allows you to formulate questions on the fly during an incident, explore issues you didn't anticipate, slice and dice the data in new ways, and save queries for future analysis or dashboards. The cost of data storage is often far, far less than the cost of a prolonged outage because you didn't have the right data point when you needed it most.
Data is cheap, downtime is expensive.
You got it. Fourth, ensure cross-cloud and on-premise debugging capabilities, especially for hybrid solutions. It's actually rare for an enterprise to be 100% in one single cloud provider, or even purely cloud anymore. You'll likely have hybrid or multi-cloud environments. Choose a monitoring or observability platform that's agnostic to where your code is hosted, whether it's on-prem in AWS, Azure, Google Cloud, wherever. This gives you consistent, unified visibility across your entire ecosystem, preventing those dangerous blind spots at the boundaries between environments. Fifth, be proactive, not reactive. Don't wait for a critical outage to finally decide to implement comprehensive monitoring and observability. The cost of robust tools is almost always offset, often many times over, by faster issue resolution and the easy identification of performance bottlenecks or inefficiencies that might otherwise go unnoticed for months, silently costing you money or customers. The only things you truly shouldn't monitor are the things you genuinely don't care about or have zero impact on your business.
Makes sense.
And finally, maybe most importantly, monitor infrastructure for application value. Don't just monitor servers for their own sake, looking at CPU and memory in isolation. Tie that infrastructure data back to the applications and services they support. Knowing the average CPU usage across all your machines in a region is far less useful than knowing the average CPU usage specifically for the machines hosting your critical checkout service in the US East region. Context is everything for debugging effectively. Your infrastructure exists to serve your applications, and your monitoring should reflect that relationship.
Now, let's talk specifically about architectures. Microservices, they've delivered immense benefits, right? Scalability, flexibility, independent deployments, fantastic stuff. But they've also fundamentally changed how we troubleshoot. If your application is decomposed into dozens, maybe even hundreds, of small independent services, how do you even begin to manage all those log files? What makes traditional localized logging, each service writing to its own file, so utterly inadequate for microservices architecture? And why does centralized logging become so utterly indispensable?
You've hit on one of the most critical operational challenges of microservices. In an architecture where each service maintains its own separate set of log files, it very quickly becomes an unmanageable mess. Chaos, really. Imagine trying to trace a single failed user request across 10, 20, maybe 100 different services, each generating logs, maybe in slightly varying formats stored on ephemeral hosts that might disappear.
Nightmare scenario.
It is. It's incredibly difficult, borderline impossible sometimes, to access, correlate, and analyze that information effectively. Root cause analysis turns into a painful, time-consuming archaeological dig. This is precisely why centralized logging is not just a nice-to-have best practice, but a truly non-negotiable imperative in any mature microservices environment. You simply can't operate effectively at scale without it. So what is it? Centralized logging is the practice of aggregating logs from all these disparate microservices, and indeed from any other sources across your infrastructure, databases, load balancers, Kubernetes clusters, into a single unified location. This consolidation provides a number of powerful strategic benefits. First, obviously, a unified view. Instead of jumping between countless individual log files or SSHing into boxes, you get a consolidated overview of logs from all your microservices, all your infrastructure, in one place. This vastly simplifies monitoring and troubleshooting because all the relevant information is correlated, providing that holistic picture we keep talking about.
One pane of glass.
Ideally, yes. Second, it enables efficient search and analysis. With logs aggregated, usually indexed, and often structured, you gain powerful search and filtering capabilities across your entire dataset. This allows for rapid problem identification. You can search for specific error codes, unique trace IDs that span multiple services, or specific user IDs across every service involved in a transaction. This massively accelerates your time to resolution. Third, it leads to improved monitoring and alerting. By integrating these aggregated logs into a central system, you enhance real-time monitoring capabilities. You can set up much more sophisticated alerts based on patterns or thresholds observed across multiple services simultaneously. This provides a more holistic and often predictive view of system health, rather than just getting isolated alerts from individual services that might miss the bigger picture.
Smarter alerts.
Much smarter. Fourth, it facilitates historical data analysis and compliance. Centralized systems are designed to store logs, often vast quantities, over extended periods. This is essential for historical analysis, identifying long-term trends, performing forensic auditing after a security incident, and crucially, meeting various compliance requirements like GDPR, HypePay, or PCI DSS by having an accessible, often immutable record of events. And finally, perhaps overlooked but very important, it results in reduced operational complexity. It streamlines log management overall. It significantly cuts down the overhead of manually managing scattered log files, rotating them, archiving them, securing them individually. This frees up your operations and development teams to focus on more strategic work, like developing new features or improving core services instead of wrangling logs.
Okay, so centralized logging isn't just about convenience. It's about providing critical context, enabling real-time insights, improving security posture, and simplifying operations. All things that are basically impossible otherwise in microservices. But for an informed team listening, the real question isn't just what it is, but how you actually put this kind of system together effectively. What are the essential building blocks? And where do teams typically stumble during implementation? What are the common pitfalls?
That's definitely where many organizations face their biggest challenges. A robust, centralized logging system comprises several key components working in concert, and missteps or weaknesses in any one can degrade the entire system's value. We typically start with log agents. These are lightweight software components, think Fluent, Logstash, FileBeat, maybe an OpenTelemetry collector installed directly on your servers or within your containers where the microservices run. Their job is simple but critical. Collect logs from various sources, application logs, Stout and Cedar, system logs, web server access logs, and reliably forward them to the centralized aggregation layer. The trick is getting them deployed consistently and configured correctly across diverse services without impacting application performance significantly.
The collection points.
Exactly. Next is log aggregation. This component, or layer, collects and consolidates logs arriving from all the different agents. It often involves tools like Logstash or Fluent again, acting in a more central role now. They can parse different log formats, process and enrich the logs, maybe adding metadata like the application name, environment, or Kubernetes pod info, and then format them consistently before sending them onto storage. This is where you might normalize different log formats into a common structured schema, like JSON, which is absolutely vital for effective downstream analysis.
Processing and standardizing.
Right. Then comes log storage. This is the central repository where all your aggregated processed logs reside. It needs to be highly scalable, cost-effective for potentially vast volumes of data, and designed for fast querying and retrieval. Common choices include specialized databases like Elasticsearch, or increasingly cloud-based object storage like Amazon S3 or Google Cloud Storage, often coupled with a query engine. The key is choosing storage that meets your retention, performance, and cost requirements. After storage, we need log analysis and visualization tools. These provide the interface for your engineers, SREs, and security teams to actually interact with the log data. They need to offer powerful searching, filtering, and aggregation capabilities to generate insights, and visualization features to create dashboards for trend analysis and anomaly detection. Tools like Kibana, often paired with Elasticsearch in the ELK stack, Grafana, or commercial platforms like Splunk are excellent examples here.
Making sense of it all.
Exactly. And finally, alerting. This component allows you to configure rules that automatically generate alerts based on specific log patterns, error counts, or thresholds observed in the aggregated log stream. These alerts need to be actionable and sent via appropriate channels, email, Slack, PagerDuty, or integrated directly with incident management systems, ensuring your teams are notified of critical issues in a timely manner without creating excessive noise. Now, implementing this, especially in a complex microservices architecture, demands careful planning. When choosing tools, you have options like the popular open source ELK stack, Elasticsearch, Logstash, Kibana, or maybe alternatives like FluentBit paired with Elasticsearch, EFK, Graylog, or commercial SaaS platforms like Splunk Cloud, Datadog, or Logs.io. Critical steps involve properly configuring your log agents to capture logs from all relevant sources consistently. It's absolutely vital to enforce consistent, structured log formats, preferably JSON, across all your microservices. This makes logs dramatically easier to parse, query, and analyze effectively later on. Standardizing logging libraries and practices helps immensely here.
Structure is key.
Absolutely. You then implement robust aggregation pipelines to process, enrich, add that valuable metadata, and reliably route these logs to your chosen storage. Setting up powerful analysis and visualization tools comes next, creating dashboards for key operational metrics derived from logs, and configuring meaningful, low-noise alerts for critical issues. And, as always, ensuring security and compliance is paramount throughout this entire pipeline. This means implementing strict access controls, who can see what logs, encrypting log data both in transit from agent to aggregator and at rest in storage, and adhering to relevant regulations like GDPR or HIPAA to protect potentially sensitive information contained within logs. Logs often contain PII or critical operational data, so they need strong protection. Now, the challenges are significant, no doubt. Managing the sheer volume of data generated by hundreds or thousands of microservices can be immense, requiring highly scalable and cost-efficient infrastructure that doesn't break the bank. Ensuring consistency in log formats across a rapidly evolving ecosystem of services, possibly built by different teams using different languages, is also a continuous challenge. It often requires strong technical leadership and governance. Constant effort.
It is. And preventing negative performance impacts on your actual microservices from the overhead of log collection and processing itself requires careful tuning and resource management of your agents and aggregation pipelines. You don't want your logging to slow down your application. So the best practice is really reiterate. Standardize your logging practices and formats early. Optimize log volume by using appropriate log levels wisely. Gotcha. Don't log debug messages in production unless actively troubleshooting. Filter out noise aggressively. Monitor and maintain your logging system itself. It's critical infrastructure too. And define clear data retention policies to manage the life cycle of your log data and control storage costs effectively. It's a continuous commitment to clarity, efficiency, and operational excellence.
That deep dive into logging, especially its necessity for microservices, sets us up perfectly for the next crucial discipline we wanted to cover: Site Reliability Engineering, or SRE. Originating at Google, we know SRE isn't just a job title. It's really a profound philosophy, a specific approach that combines software development principles with IT operations practices. For our listeners, what's truly at SRE's core, and how does it fundamentally shift the mindset away from traditional IT operations?
You're right, it's much more than just a role. SRE's core mission is essentially to apply software engineering principles, data-driven decision-making, automation, systematic problem-solving to operations problems. It's about building and managing scalable, highly reliable, and efficient systems. There's a relentless focus on reducing downtime and toil that's the manual, repetitive operational work through automation, proactive monitoring, and rigorous, data-driven incident response. The fundamental mindset shift is moving away from just keeping the lights on reactively to proactively asking, how can we design, build, and automate the system so the lights never flicker in the first place? Or, if they do, how can the system recover almost instantly, often without human intervention? It's about treating operational challenges not just as tasks to be done, but as engineering problems that can be solved, often permanently, with code, with data analysis, and with systematic processes.
So, connecting this back to the bigger picture, SRE isn't just about firefighting or keeping things running day to day. It's about architecting and engineering for resilience from the ground up, making sure the lights never flicker or recover almost instantly, even as the system grows exponentially in scale and complexity. It sounds like a commitment to engineering perfection applied to operations.
That's a great way to put it. A commitment to engineered reliability. And this mission is underpinned by several core principles that directly impact cloud service availability and resilience in very tangible ways. First, and perhaps most famous, is the concept of error budgets. This is a real game changer introduced by SRE. An error budget defines an acceptable level of downtime or failure for a service, usually derived from its service level objective, or SLO.
Okay, so how much failure is okay?
Exactly. It quantifies how much unavailability is tolerable over a given period, typically a month or a quarter. This is critical because it forces a data-driven balance between developing new features and maintaining reliability. If your service is consuming its error budget too quickly, meaning it's less reliable than the agreed-upon target, development teams must stop releasing new features and focus solely on reliability improvements until the service is back within budget. Conversely, if you consistently stay well within your error budget, you have more confidence and justification to innovate and release faster. It explicitly aligns development velocity with service reliability using a shared metric.
That's fascinating. So an error budget isn't just a target. It's like a contract, a quantifiable agreement between engineering, product, and the business that directly influences priorities and resource allocation based on actual performance. That's a powerful mechanism.
It absolutely is. It replaces subjective arguments with objective data. Second, automation is absolutely central to the SRE philosophy and practice. Automating tasks like monitoring setup, provisioning infrastructure, running incident response playbooks, performing system upgrades, handling capacity scaling, and even routine maintenance dramatically reduces the potential for human error. It also frees up highly skilled engineers from tedious, repetitive work, toil, so they can focus on more complex, higher-value engineering problems. This increases operational efficiency, enables systems to potentially auto-recover from certain types of failures without any human intervention, and allows for real-time automated scaling of cloud resources based on varying workloads. For instance, automated scripts can detect performance degradation and trigger the addition of new instances to a cluster to balance the load, all without waking someone up at 3 a.m.
Reducing toil, increasing consistency.
Exactly. Third, monitoring and observability are foundational. SRE relies heavily on comprehensive real-time monitoring of key performance indicators, KPIs, things like uptime, latency, response times, throughput, saturation, and error rates. These are often tied directly to the SLOs. But as we discussed earlier, SRE goes beyond basic monitoring into deep observability. It leverages those correlated logs, metrics, and traces to gain profound insights into the internal state and behavior of the system. This enables SRE teams to proactively identify and resolve potential issues before they affect end users, often predicting potential failures based on subtle trend analysis or resource consumption patterns. And fourth, a crucial cultural element, blameless postmortems and continuous improvement. When failures inevitably occur because no complex system is perfect, SRE emphasizes conducting detailed, blameless postmortems. These analyses focus on understanding the systemic root causes of incidents. The focus is not on who made a mistake, but on what in the system, the tooling, or the processes allowed the mistake to occur or failed to prevent its impact.
Focus on the system, not the person.
Precisely. The outcome is the implementation of concrete, long-term fixes to prevent recurrence. This fosters a culture of psychological safety and ensures that every incident, every outage, becomes a valuable learning opportunity to improve the overall resilience and availability of the cloud services. It drives continuous improvement. Now, the impact of these SRE practices on cloud service availability is significant and very direct. For instance, SRE leads directly to reduced downtime. How? Through that continuous tracking of performance, resource usage, and potential threats, combined with automated responses. Early detection and automated remediation minimize disruptions. Automated load balancers, as we mentioned, can instantly redistribute traffic to avoid overloads, keeping services available even during unexpected traffic spikes. It also ensures enhanced fault tolerance and redundancy. SRE actively promotes and implements techniques like data replication, duplicating data across multiple servers or regions, and automated failover, automatically redirecting traffic or processes to healthy backup servers if a primary one fails. Redundancy means backup systems are designed and tested to automatically kick in during outages, ensuring service continuity with minimal interruption.
Building in resilience.
Exactly.
Yeah.
Furthermore, SRE is key to achieving true scalability and elasticity in the cloud. SRE practices ensure systems can not only handle growing workloads over time, scalability, but can also automatically adjust resources up or down based on real-time demand, elasticity. This prevents performance bottlenecks during peak times and avoids wasteful over-provisioning during quiet periods, maintaining optimal service levels efficiently. In fact, SRE automation demonstrably improves several key operational metrics. Obviously, downtime reduction as systems recover faster or avoid outages altogether, improved response time through dynamic resource allocation and performance tuning, higher SLA adherence thanks to effective SLO management and error budgets, and optimized resource utilization as automated scaling precisely adapts to real-time demand, improving cost efficiency. Let's look at a few SRE practices in action, just to make this more concrete. Incident response and root cause analysis is a core SRE function day-to-day. When an alert fires, SRE teams use their comprehensive monitoring tools and runbooks to quickly detect, diagnose, and respond to failures. After the immediate fire is out, they conduct that thorough root cause analysis, RCA, to understand why it happened and implement those long-term fixes, meticulously documenting every step in the post-mortem. To minimize the risk and downtime associated with software updates, SRE implements techniques like automated rollbacks and canary deployments. Automated rollbacks allow a system to quickly and safely revert to a known stable previous version if a new deployment starts causing problems, often triggered automatically by monitoring detecting increased error rates. Canary deployments, on the other hand, release new features gradually, starting with a very small subset of users or servers, while closely monitoring performance and error metrics. If all looks good, the release progressively rolls out to larger groups, minimizing the potential impact of any unforeseen bugs.
Safer deployments.
Much safer. Capacity planning and load balancing are also crucial ongoing SRE activities. SRE teams use predictive models, often based on historical usage patterns and business forecasts, to estimate future resource needs and proactively provision capacity. They employ sophisticated load balancing techniques to distribute incoming traffic evenly across multiple servers or service instances, preventing single points of failure and ensuring consistent performance, even under extreme load conditions.
Those benefits are undeniably compelling, offering a clear path to achieving unprecedented reliability and efficiency in complex cloud environments. But let's be realistic, implementing SRE sounds like a significant cultural and technical undertaking. What are some of the most challenging hurdles organizations typically face when trying to adopt and implement SRE practices, particularly in a cloud-first or hybrid environment?
You're right to ask. The hurdles are indeed significant, and interestingly, they're often more cultural and organizational than purely technical. One of the biggest, perhaps the biggest, is achieving the necessary cultural shift. True SRE requires breaking down the traditional silos that often exist between development teams, who want to ship features fast, and operations teams, who want stability. It demands deep collaboration, shared ownership, and shared responsibility for system health and reliability. Moving from a throw-it-over-the-wall mentality to a we build it, we run it, we own its reliability together mindset requires strong leadership buy-in, consistent reinforcement, and sustained effort to change deeply entrenched behaviors and incentives. It's not easy.
Changing habits is hard.
Very hard. There's also the tangible cost of redundancy. While absolutely essential for achieving high reliability, designing, implementing, and maintaining robust backup systems, geographically distributed replicas, additional data centers, or complex automated failover solutions across a cloud environment can be resource intensive. It leads to higher operational costs compared to a less resilient setup. It's a necessary investment for resilience, but that cost needs to be clearly understood, justified based on business risk, and managed carefully within budget constraints. Reliability isn't free. And finally, related to our earlier discussion, the sheer complexity in monitoring and managing distributed systems. As we've discussed, modern cloud environments are often highly distributed, dynamic, and composed of many interconnected, often ephemeral components. Effectively monitoring, troubleshooting, and managing this complexity requires incredibly sophisticated observability tools and, critically, a highly skilled SRE team capable of interpreting the data and navigating this intricate landscape. It's not a set-it-and-forget-it solution. SRE requires continuous learning, adaptation, and investment in both tooling and people. Finding and retaining those skilled SREs can also be a challenge in itself.
Okay, we've explored the immense power and insight that comprehensive logging, monitoring, and SRE practices provide for reliability and performance. Fantastic stuff. But as anyone who's ever received a surprisingly large cloud bill knows, all this power, all this data comes with a price tag. It's remarkably easy for cloud costs, especially around logging and monitoring, which generate data, to spiral out of control if you're not vigilant. So what are the key strategies? How do we keep our cloud logging costs from ballooning while still getting the essential insights we need for operational excellence and reliability?
That's such a critical balancing act, isn't it? Because the very systems providing visibility into your costs and performance can themselves become a significant cost center if not managed intelligently. And the good news is these cost management principles we'll discuss are pretty universal. They apply whether you're using Google Cloud Logging, AWS CloudWatch, Azure Monitor, a third-party SaaS tool, or even managing an on-premise logging solution. The concepts are the same. The very first step is fundamental but sometimes overlooked. Analyze your current spending. You need a detailed, itemized understanding of what volume of log data is going where and exactly what it's costing you at each stage. Look for the obvious cost components in your cloud billing reports. Things like log volume, ingested the cost just to receive and initially process the log data, often priced per gigabyte, and then log storage volume, the cost to retain those logs beyond any default free tier or included retention period, typically 30 days. This is also usually priced per gigabyte per month.
Ingestion and storage. Got it.
All right, those are the big two. But don't stop there. You also need to include costs from any external third-party log management tools you might be using their subscription fees. And if you're self-hosting part of your logging stack, like running your own Elasticsearch cluster, you have to factor in the related hardware, compute instances, attached disk costs, and network bandwidth consumed by that cluster. Don't forget export costs if you're sending logs to other services like Cloud Object Storage, S3, GCS, or data warehouses like BigQuery or Redshift for long-term archival or analysis. And there might be processing costs for streaming tools used in your pipeline, like Kafka, Kinesis, PubSub, or Dataflow, including potentially significant network egress charges if logs are moving between different cloud regions or out to the internet. And critically, try to account for the hidden costs, the valuable engineering time your team spends managing, maintaining, upgrading, and troubleshooting all these logging tools and pipelines. That people cost can often dwarf the direct infrastructure costs.
Yeah, that's a really holistic view. It's about looking beyond just the sticker price of the logging service itself and really digging into the entire lifecycle cost, including that crucial human element.
Exactly. You need the full picture. Once you have that clear understanding of your current spend, step 2 is where the real optimization begins. Eliminate waste, don't pay for logs you don't need. Optimizing your log volume at the source or as early in the pipeline as possible is almost always the single most effective way to reduce your overall logging spend. Even if you have a fixed contract price with a vendor based on total volume, reducing unnecessary volume can still cut down on processing costs within your pipeline, improve query performance for the logs you do keep, and maybe allow you to stay within a lower contract tier next renewal.
Less data, less cost, faster queries.
Yeah.
Makes sense.
Right. So how do you do this? First, you need to find the chatty logs. Identify which applications, services, or infrastructure components are generating the highest volume of logs. You'd typically use your cloud provider's built-in monitoring dashboards or metrics explorers to find this information. For instance, in Google Cloud, you might look at Cloud Monitoring's dashboards or use Metrics Explorer with the logging.googlelepus.com for billing bytes ingested metric. In AWS, you'd look at CloudWatch logs metrics for incoming bytes. The principle is identifying the equivalent billing or ingestion volume metric in whatever cloud or tool you're using.
Find the noisy neighbors.
Exactly. Once you know what logs are the chattiest, you can start using routers and filters strategically to reduce the volume you actually ingest or store long term. A common example is avoiding sending the same logs, like audit logs, to multiple different storage destinations if a central security team already collects and manages them in a dedicated security information and event management SIEM system. You can often use exclusion filters on your default log syncs or routing rules to prevent this duplication. Similarly, if you're paying for an expensive external log management tool, think carefully about whether you also need to save the exact same logs redundantly in your primary cloud provider's logging solution, like CloudWatch or Cloud Logging. Maybe keeping a small, critical subset of system or application logs there for immediate troubleshooting or support access is sufficient, but filter out the rest to avoid paying twice.
Deduplication is key.
Absolutely. Another powerful technique, especially for very high volume but potentially lower value logs, is to sample the chatty logs. For instance, maybe you don't need every single successful 2xx status code health check log from your load balancer every second. Perhaps sampling 10% or even 1% of those logs gives you enough visibility for monitoring trends while drastically cutting volume and cost. This needs careful design, though you need to think about your specific usage patterns, security requirements, and any compliance mandates before you start sampling critical logs.
Needs careful consideration.
Definitely. Step 3 is to optimize costs over the life cycle of your logs. This really boils down to avoiding storing logs for longer than you absolutely need them in expensive, immediately queryable storage. Review your retention policies regularly. For many cloud logging services, like Google Cloud Logging, for example, doubling the default retention period, say from 30 days to 60 days, might only increase the storage cost component by a relatively small percentage, maybe just 2% or so, for those logs retained longer than the initial free or included tier. And you can usually change these custom retention periods easily at any time. However, keeping logs for years in hot searchable storage can become very expensive. Consider tiered storage options. Keep recent logs, for example 30-90 days, hot for operational troubleshooting. Move older logs to cheaper, maybe less immediately queryable archive storage like S3 Glacier or GCS Archive for compliance or occasional forensic analysis, and delete logs entirely once they are no longer needed according to your policy. It's always a good idea to compare the retention costs if you're storing logs outside your primary cloud logging service, for example, rolling your own archive on object storage, to ensure you're getting the best value for long-term archival.
Match the storage cost to the access needs.
Precisely. Finally, step 4. Set up alerts to avoid surprise builds. Once you've gone through steps 1 through 3 and you're confident that the volume of logs being ingested and retained fits within your budget, configure automated alerts for any sudden, unexpected spikes in volume before they lead to unexpectedly large bills at the end of the month. You can usually set these alerts based on the billing metrics for ingested log volume, like that bytes ingested metric we mentioned, or potentially on the volume of data being routed to specific expensive sinks like message queues, PubSub, Kinesis, or data warehouses, BigQuery, Redshift. This proactive alerting acts as a safety net, ensuring you maintain control over your spending and aren't caught completely off guard by a runaway application or misconfiguration generating terabytes of logs.
A budget guardrail.
Exactly. And just circling back to tooling, it's worth noting again that using the integrated cloud operations tools provided by your cloud vendor can often provide more value and better cost control in this area. An IDC report actually found that over 50% of respondents preferred using their public cloud providers' monitoring tools over third-party alternatives, citing advantages like scalable log router functionality, often being included at no extra charge, which significantly contributes to budget optimization by letting you filter and route logs efficiently before they even hit the expensive ingestion or storage layers. The more natively integrated your tools, often the more efficiently you can manage this data flow and its associated costs. ###neat, modernization, security, and the horizon of cloud operations.
Wow, okay. We've covered so much ground today, from the fundamental data types and collection methods through the proactive power of observability and the engineering discipline of SRE, right into the practicalities of intelligent cost management. Fantastic insights. But the cloud, as we know, is a landscape that's constantly relentlessly evolving. How do we ensure our systems, our monitoring, our operational practices remain modern and secure? How do we continually adapt without hitting major roadblocks or just falling behind the curve? And maybe what's exciting on the horizon for cloud operations?
That's the million-dollar question, isn't it? It's about continuous learning and building future-proof monitoring and operational solutions that can gracefully adapt to this ever-changing modern cloud landscape. One key shift we absolutely must account for in our tooling and thinking is that pets versus cattle analogy we touched on earlier. On-premise servers were often treated like unique pets, individually named, configured, meticulously cared for. Cloud VMs, Docker containers, serverless functions, they are cattle. They're designed to be interchangeable, ephemeral resources that can be spun up, scaled out, and torn down automatically, sometimes in seconds.
Disposable infrastructure.
In a way, yes. Your monitoring and observability needs to handle both paradigms gracefully. It needs to provide deep visibility into an individual instance or container when necessary for troubleshooting. But more importantly, it needs to focus on the aggregate health of the herd, using dynamic filtering, tagging, and service discovery to make sense of these constantly changing transient components. Static dashboards based on fixed host names just don't work anymore. Also, platform components matter more than ever before. In the cloud, your application isn't just your code running on a VM you manage. Cloud platform components, things like managed load balancers, ALBs, NLBs, managed caches, Redis, Memcached, serverless databases, DynamoDB, Firestore, message queues, SQS, PubSub. These are integral, often critical parts of your application's overall architecture and performance.
It's a part of the stack now.
Absolutely. They must be monitored rigorously, and crucially, the data from these platform services needs to be tied back contextually to the specific applications or services they support to derive their true operational value. A slow-managed database isn't just an abstract database problem, it's directly impacting the performance of the specific applications relying on it, and your observability needs to show that connection clearly. Critically, especially for larger organizations, aim for vendor agnosticism where practical in your monitoring and observability strategy. Try to avoid locking your core observability capabilities entirely into a single cloud infrastructure vendor's proprietary tools if you anticipate a multi-cloud or hybrid future. Choosing a platform, whether open source based or a commercial vendor that natively supports multi-cloud, AWS, Azure, GCP, and hybrid environments gives you much greater flexibility. It allows you to leverage innovations or cost advantages from different providers or move workloads between environments without having to completely rip and replace your entire observability stack, which would be a massive, costly re-engineering effort.
Keeps your options open.
Exactly. And finally, a strategic point. Monitor your business, not just your infrastructure or applications in isolation. As the cloud continues to abstract away more of the underlying infrastructure concerns, your teams, dev, ops, SRE, product, can and should shift focus higher up the stack towards business-level metrics. Use extensible observability tools that allow you to easily track custom metrics, business transaction attributes, and key user journey events. This lets you directly correlate system performance, application features, and operational health to tangible key business outcomes, things like user conversion rates, customer satisfaction scores, NPS, cart abandonment rates, or even revenue per minute during peak sales events. This is where operations truly meets business strategy and demonstrates its value.
Connecting the tech to the dollars.
Precisely. Now, diving specifically into security, which is intrinsically linked to reliability and availability, having a robust cloud security alert system is absolutely non-negotiable today. Based on common best practices, here are about 7 critical pillars for an informed team to consider. First, real-time monitoring is paramount. You need immediate visibility into potential threats for faster detection and response. Native cloud tools like AWS Cloud Watch events, Azure Monitor alerts, or Google Cloud Audit logs provide instant alerts for suspicious API call, configuration changes, or unusual login activities. Critically, integrating AI-powered security analytics tools here can significantly enhance this by identifying complex attack patterns, drastically reducing the noise from false alarms, and prioritizing threats based on actual risk severity, allowing your security teams to focus their limited attention on genuine threats.
Cut through the noise.
Yes. Second, establish clear automated alerts with well-defined severity categorization. May be critical, immediate action needed, warning, investigate soon, and informational, situational awareness. These automated alerts should integrate tightly with your security information and event management, or SIEM, tools for centralized correlation and investigation. Using machine learning and anomaly detection techniques here can proactively spot threats that deviate significantly from established normal behavior baselines, again reducing false positives and ensuring only the most urgent and credible issues trigger high-priority alerts. Third, regular audits are key to ensuring ongoing effectiveness. Conduct rigorous reviews quarterly as common, maybe even monthly, for high-risk environments of your security configurations, access controls, IAM policies,
Yeah.
firewall rules, and your incident response strategies and playbooks. This ensures your alert system remains effective, adapts to new threats and evolving cloud services, and stays compliant with relevant industry standards like SOC 2, ISO 27001, or IPAPE.
Keep things tuned up.
Exactly. Fourth, deploy and properly leverage SIEM tools, security information and event management. These systems are designed to centralize and analyze security data from potentially hundreds of disparate sources across your entire enterprise: cloud logs, network devices, endpoint security tools, application logs. They offer real-time threat detection through correlation rules, efficient incident response workflows, and often use AML for advanced threat correlation across seemingly unrelated events. They also greatly simplify compliance reporting by creating detailed, centralized audit trails. Fifth, practice robust log security itself. As we've discussed, logs are the lifeblood of any security investigation and compliance program, but they often contain sensitive operational data or even PII. You must protect them. Encrypt logs both in transit, as they move from source to storage, and at rest while stored. Implement strict role-based access controls, RBAC, to limit who can view or modify logs. Centralize secure storage in resilient, tamper-evident locations. And ensure your log handling practices align with compliance standards like GDPR's data minimization and access control requirements. Protecting the logs is as important as generating them.
Secure the evidence.
Precisely. Sixth, utilize CSPM tools, Cloud Security Posture Management. These specialized tools continuously monitor and assess the security posture and risks across your cloud environments: AWS, Azure, GCP. They use advanced analytics and often machine learning to automatically identify misconfigurations, security vulnerabilities like overly permissive firewall rules or unencrypted storage buckets, and ensure compliance with security best practices and regulatory frameworks. They typically prioritize alerts based on urgency and potential impact, helping security teams focus on fixing the most critical weaknesses first across potentially vast cloud estates. And seventh, don't forget penetration testing. Conduct regular tests, maybe annually or after major changes, simulating real-world attacks to proactively uncover weaknesses in your cloud infrastructure, applications, and security alerting systems before malicious actors exploit them. Different types exist: black box, no prior knowledge; white box, full knowledge; gray box, some knowledge. The findings from these tests provide invaluable real-world feedback to fine-tune your alert systems, validate your defenses, identify blind spots, and focus remediation efforts on the most critical, exploitable vulnerabilities.
That's a really comprehensive defense-in-depth strategy. It's truly sobering when you consider those statistics. I think I read some of the studies consistently show upwards of 90% of organizations have faced security breaches or major misconfiguration incidents in the cloud. These practices aren't just good-to-haves anymore, are they? They seem absolutely vital for survival in today's digital economy, where a significant breach can genuinely dismantle a business.
They truly are the modern front line of defense. There's no room for complacency. And looking just a bit further out to the horizon, the future of SRE and cloud operations as a whole looks set to be shaped by some really exciting, potentially transformative trends. Expect to see much wider adoption and sophistication of AI-driven SRE tools, sometimes called AI ops. AI and machine learning won't just analyze past data, they will increasingly move SRE from being reactive or even just proactive towards being predictive. Predicting potential outages based on subtle precursor signals, identifying performance bottlenecks before they impact users, and even automating complex remediation actions before any significant user impact occurs. ML will analyze vast amounts of historical telemetry data to continuously fine-tune auto-scaling policies, capacity planning, and anomaly detection thresholds, making systems inherently more resilient and efficient with less human intervention.
Smarter systems, less firefighting.
That's the goal. SRE will also continue to evolve and become even more critical for multi-cloud and hybrid environments. As more businesses strategically adopt multi-cloud or hybrid cloud strategies for reasons like cost optimization, feature differentiation, or risk mitigation, SRE practices will be absolutely crucial for managing availability, performance, and consistency across these disparate providers: AWS, Azure, Google Cloud, as well as potentially complex on-premise systems. This will demand even more sophisticated, unified monitoring, observability, and cross-cloud orchestration capabilities to provide that seamless end-user experience, regardless of where the underlying services are hosted. There will also be an ever-increasing focus on security and compliance integrated directly into SRE, often called DevSecOps. As we've established, security incidents directly impact availability and reliability. So future SRE practices will need to deeply integrate advanced security measures, things like automated security scanning and CI/CD pipelines, real-time threat detection within operational monitoring, continuous compliance validation, and automated security patching as foundational elements throughout the entire service lifecycle. Security won't be a separate team's problem. It will be engineered in as a core responsibility of SRE and development teams.
Security is code. Reliability is code.
Exactly. And finally, building on everything we've discussed, we'll likely see a continued acceleration towards observability-driven development. Going beyond even today's advanced monitoring, future SRE and development practices will rely on even deeper, richer observability data to understand not just what is happening in their complex distributed systems, but fundamentally why it's happening at every layer of the stack. Granular, high-cardinality data from logs, metrics, distributed traces, and maybe even newer signals like continuous profiling will enable more effective troubleshooting, performance optimization, and ultimately more informed decision-making around system design and feature development. Every deployment, every change becomes a more data-driven, lower-risk endeavor. Ultimately, SRE isn't just about maximizing system uptime anymore. It's about fostering a culture of engineering excellence, driving innovation safely, building resilient systems, and enabling continuous improvement, all while leveraging future technology like AI to navigate the increasing complexity of modern cloud infrastructure with confidence and a clear data-driven understanding. Hashtag tech outro.
Wow, that was quite a journey. We've really gone deep today through the astounding scale of the cloud, dissecting the critical differences and synergies between logs, metrics, and traces, exploring those essential early warning metrics, and truly understanding the proactive power of observability compared to traditional monitoring. We dove into the engineering discipline of SRE and its core principles like error budgets and automation. We tackled vital strategies for intelligent cloud cost management, always a hot topic. And we looked at how to keep our cloud operations modernized and secure, even peering into that transformative future driven by AI and observability. It's crystal clear, isn't it? The cloud isn't just a passive place to store data anymore. It's this incredibly dynamic, complex ecosystem that demands intelligent, proactive, and continuously evolving management practices.
Absolutely. And that leads to a perhaps provocative thought for you, our listener, to maybe ponder on your own time. In a world where AI is rapidly, fundamentally changing how we monitor, analyze, and maintain our complex systems, how might the role of the skilled human operator, the SRE, the ops engineer, the developer evolve? Will it shift primarily from being the firefighter who reacts to incidents towards becoming more of an orchestrator of intelligent systems, someone who guides, trains, tunes, and enhances these automated monitoring and remediation systems in the relentless pursuit of near-perfect cloud availability and resilience? It suggests a fundamental shift in our relationship with technology and operations, one that will undoubtedly require new skills, new tools, and certainly new ways of thinking.
That's a truly fascinating question to consider. What does the human role look like when the machines get smarter? Something for all of us in the tech world to think about as we shape our own cloud strategies and decide where these powerful insights can be applied. We certainly encourage you to explore more about advanced observability tools, delve deeper into SRE principles, and consider how they can empower your own cloud journey and transform how you manage your critical digital assets. And before we sign off, a final sincere thank you to our sponsor for this deep dive, Stonefly. For those of you looking for robust, highly secure storage solutions, perhaps consider Stonefly's specific offer. The 100 TB immutable and air-gapped SSO NAS, currently available for $8,995. Now that's a powerful solution, offering several key benefits rolled into one. Immutable storage, which is crucial for ransomware protection, optional air-gapped isolation for ultimate security against network threats, and single sign-on SSO capabilities for streamlined, secure access management to your critical data. It sounds like a fantastic option for protecting what matters most in today's challenging threat landscape. You can find out much more at stonefly.com. That's stonefly.com. Thank you so much for joining us on this deep dive into navigating the cloud with logging, monitoring, and SRE. We hope you found it valuable. We look forward to our next exploration right here on TechDaily.ai.